Hey, I told you I wanted to demonstrate a DEM of difference. And so what I'm working with here is lidar data, it's half meter data, and then I've got a 5 meter photogrammetry data. And I start by resampling the 5 meter down to the half meter because I want to preserve the detail that I have in the lidar data set. So using the resample tool, my input raster is the 5 meter photogrammetry. I'm resampling it down to half meter. I can make the output cell size match the lidar data set. It's continuous data, so I'm going to choose bilinear. But the important thing here is you want to go into the, the snap raster and force the resampled cells to snap or align with the lidar. So the 5 meter, as it's resampled, is going to come out matching that exactly. Okay, so after running the resample of the 5 meter data, we can minus them. This is one of those instances where there's multiple toolboxes. So we are going to subtract the resampled half-meter version of the autocorrelated data from the lidar. We'll go ahead and just stick it here. But in the environment setting, we can limit, because the 5 meter tile is so much bigger, we can limit the processing extent to just the lidar tile. And it's probably, I don't know, we've already snapped it, but let's just make sure it's all snapped together. Okay, we can turn off our inputs, and we did constrain the final size. We've got a range of values like this, and I'm going to go ahead and symbolize that. Okay, I'm using this color scheme here. I'm going to change this to something that's a little bit easier to see against the hillshade. Get rid of these in-between ones and get rid of that purple and kind of make it more of a rosy color. And then we'll customize the range here so that we're going from 113 meters of difference to minus 113 meters of difference, so that we're forcing that middle color, or no change in the elevations, to white. Okay, so I did a little symbology action on this. Like I said, changed this to a rose color. I did set the middle color to 0 change, and then verified by using the Explorer tool to go in and sample the elevations across this middle gradient and the lightest colors to make sure that just barely higher lidar is a little bit orange, and then the little bit rosy pink is where the autocorrelated DEM was reading as higher. So right now I put a layer blend on this DEM of difference over the hillshade, but we can use the swipe tool to kind of inspect the autocorrelated or 5 meter hillshade that's beneath. So you can see in this big orange patch right here underneath, you can see that the 5 meter data, the autocorrelated data, just kind of cut off the top of that peak and flattened it. And so in the orange areas, the lidar is reading as higher. In the purple areas, the photogrammetry, autocorrelated DEM, is reading as higher. And so here you can see this ravine, or this lower area, may have been vegetated, and you can see that the surface is higher than the lidar, is indicating that the surface really is. And then along this kind of erosional edge here, it's just kind of messy, but I think it's interesting right here. You can see that the lidar is reading higher because, and it's lidar is reading higher all the way down this slope, but the 5 meter DEM is showing the ridge further to the west. You can see the ridge line runs like this on the 5 meter data. That's kind of a big error. Yeah, so the whole point of this is to sort of demonstrate the low quality of that autocorrelated data. It has its purposes, but I would never use it for calculating any kind of surface analyses or flow analyses on a landscape. I think it's important to point out that the units on this, the units are meters. So there are places on this small, lidar tile where the lidar is reading 112.5 meters higher than the autocorrelated DEM is. 112 meters. And then there are places where the autocorrelated DEM is reading 65 meters higher. So this is a lot of difference, and needs to be taken seriously, I think, when choosing what kind of DEM to use for your analyses.